So now we're into our second lecture in Chapter 12 dealing with thermal radiation. Again, we're understanding the wavelength characteristics, the directional characteristics of thermal radiation, understanding properties like emissivity, absorptivity, reflectivity. To characterize it, they can be a function of wavelength, they can be a function of direction as well. We covered a lot of ground. There's still a lot of ground to cover. Let's continue into the material. Focus on an area. Let's just draw it like a line. Okay, this area maybe has some depth to it. Maybe there's some heat transfer that can happen on the backside. Maybe conduction to supply heat. And so instead of just having it a conductive heat transfer, we'll talk about maybe conductive flux or some energy balance on the backside to maintain that surface's temperature. So this surface can emit some radiation. Often they draw it with a little bit of a wiggly line coming off at an angle. So that would be some emission coming from the surface. All right. You can also have radiation coming to the surface. So not only do you have emission, but you have irradiation. So we draw a squiggly line with radiation coming to the surface. Now, because we don't want to talk about the size of the surface, we're going to talk about the emissive power in funny units of watts per meter squared. I'd prefer to call it emissive flux, but the book uses emissive power, so I'm not going to try and confuse you. But this has watts per meter squared. What about this one coming in? They give it the symbol G for irradiation, and the units watts per meter squared. What do you mean per meter? Per meter squared of the area that the photons are hitting, coming from another location, somewhere else. And then likewise, Q double prime, you can tell already it's watts per meter squared of that area. It's obvious that with the double prime that it's a flux. Well, what happens to some of the incoming radiation? Some of it gets absorbed. It's like alpha G gets absorbed. Alpha is the absorptivity of that surface, but some of it gets reflected. And so we would call that rho G. What was rho a symbol for? Reflectivity. It's a percent that's reflected. And now you're saying, I have some part of the photons coming off of a surface are due to the emission. Some of the photons coming off of a surface are due to reflection. And the net outgoing is called the radiosity. Radiosity. New word. Hey, this class is just all new vocabulary, isn't it? Well, sorry, engineers try and make it as simple as possible, but then they have to have new terms and new words to quantify the stuff. Radiosity. And the symbol J is used for the outgoing net flux. It has the same units of watts per meter squared, and so it's the sum of the reflected plus the emitted. What we can do is introduce a large system control volume like this. Come up here, cut it through there, come across, cut it through there, and come down and close it in. So there's a large control volume. And what you have is the ins must equal to the rate at which it's flowing out. The ins are equal to the outs. All right, so everything is per unit area. So what are one of the ins? Q double prime from the backside. Think of this as being supplied to maintain the surface at a particular temperature. Okay. Then we have another in of G. Now I wish the book used the G double prime because then it would be a flux, but nope, sorry. So right away the equation looks a little awkward without the double prime on all the terms. But they have the same units, watts per meter squared. And then what's the out? The J. The J is the out. Okay. Well, we can expand. What is the J? The J is, the radiosity is the reflectivity times the incoming. And then we have the emission. This emission you can characterize by saying it's the emissivity of the surface, how well it emits, times the black body emissive power. We are only going to focus on opaque surfaces. If it's an opaque, then we recall that the sum of the absorptivity and the reflectivity and the transmissivity is equal to 100%, but for opaque, there's no transmission. It's either absorbed or reflected. Okay? So what we can do here, let me just leave this G right there for a second. Now I'm going to bring that G to the other side. That's equal to rho minus 1 times G Q double prime. Okay, this is rho minus 1, reflectivity minus 1. If I come up over here, I bring this reflectivity to this side. Don't I have 1 minus rho? So if I can do a little algebra, that's just minus alpha G plus epsilon EB Q double prime. Now this is going to be the launching point for Kirchhoff's law that we're going to establish. And you can just read this. So what you have is you have the emissivity times the black body emissive power minus the alpha, the absorptivity, times G, the incoming radiation. So Kirchhoff's law, you can derive it for a little surface and a big surface. That's often done in the textbooks. I like to just do it for two large parallel plates. And these two large parallel plates are at temperature T1 there and temperature T2. Now, we're interested in maybe the flow of heat, the heat flux between the two, the radiative exchange between the two. Now, if the temperature of the one is equal to the temperature of the two, what do you think Q double prime is going to be if they're the same temperature? 0. But what's happening, you're correct, what's happening is you do have emission coming from this one. And so let's call that emission from 1. But where does the emission from 1 go? It can only go and hit 2. It can, radiation goes in a straight line. The photons just go straight until they hit something and interact some way. So when you, from the perspective of 2, guess what G2 is, the incoming into 2? It's equal to the outgoing from 1. See that? And likewise, you come over here and you say, well, what's the emission from 2? And both of these I should have said are black to begin with, black. So that I don't have any reflection. So you just have the emission from 1 is the incoming to 2. And likewise, the emission from 2, where is that going to go? And it's going to be the incoming to 1, right? So let's take and recall what we had before. We had the Q double prime focus on surface 1, Q double prime on 1 is equal to the emissivity E1 minus absorptivity G1. Okay. If they're black, then this really boils down to almost nothing. Basically, it's 1 times, then you have the EB1 minus, and then you have the absorptivity is 1, and then EB of 1, which G1 is EB2. You just basically get that T1 to the 4th minus T2 to the 4th. If they're the same temperature, what is Q double prime? Has to be 0. It has to be 0. All right. Now let's step it up a notch. Let's say that surface 1 is not black, but surface 2 remains black. Okay? So surface 2 is a perfect absorber, perfect emitter. Surface 1 has emissivity. Okay, so let's go and say, well, what's my heat flux for surface 1? Well, I'm going to have the emissivity of surface 1 times that black body emission, EB1. I should have put an EB1 right there. I did put it right there, didn't I? Here, just fine. EB1. Okay, and then we're going to have alpha 1 times G1. What is G1? It's going to be EB2, isn't it? These have the same temperature. If T1 is equal to T2, then we conclude epsilon 1 minus alpha 1 times sigma t1 to the fourth or t2 to the fourth. It doesn't matter. T1 is equal to t2. Okay, Q1 double prime. If these two temperatures are the same, Q double prime is 0. It has to stay 0. This can't be 0. The only thing in the equation that can make this equation work is that epsilon 1 must be equal to alpha 1. That's the logic in the derivation of Kirchhoff's law. If you ask somebody to write down Kirchhoff's law, they'd say, well, for a surface, the emissivity of the surface is equal to the absorptivity of the surface. And that probably I would accept. I wouldn't quibble with them a little bit. But what happens is, you know about the wavelength characteristic of light? It's really at any particular wavelength. It's like the monochromatic emissivity is equal to the monochromatic absorptivity. If they said something like that, I'd give them a double thumbs up and say, hey, you're pretty smart. You know about the wavelength characteristics of light. Then if somebody said, and that's not only that, it's the emissivity at a particular wavelength and at a particular temperature of the surface and particular angle theta and phi, which characterizes its directional characteristics. And you know what? I'd say you really studied Kirchhoff's law, because now you really know that it's not just epsilon equal to alpha, but it's at every single wavelength, at every temperature of that surface, in every direction characterized by that phi and alpha. The same thing for the outgoing. So let's just leave it at that. This is kind of more of a graduate discussion. I did this last time, did I not? X, Y, do this again in review, or in 3D, the X, Y, Z coordinate system. And we talked about a line starting at the origin going out of length R. And if you take and rotate that line, it sweeps a length of the arc L, and you rotate it by a certain amount theta. And the definition of that angle of rotation, theta, is the length of the arc divided by the radius that stayed constant during the sweep. It was measured in radians. Somebody says, what are dimensions of radians? Dimensionless, it's length over length. But we like to say it's this many radians for the angle. And this is a planar angle, a 2D angle. In review, if somebody said, I want to start with here and rotate it such that it's right there, what would be the angle? Theta. Theta is how many radians? Pi over 2. And somebody says, the other case of interest is I start here and I rotate it such that I end there. The angle of rotation to go half of a circle, half, like hemicircle. Nobody says hemicircle, it's half of a circle, right? Half of a circle is pi. Then we come over here and we have the same idea. We come out a distance, maybe I'll leave it color blue, R. And we don't sweep it one way, we sweep it the other way, we sweep it the other way, and we come out with an area on the end. That area is not a planar area, it has some concavity to it. It's actually a portion of the segment of a sphere. And then we talk about this being not just an easy angle to do, but a solid angle, omega. And that omega angle is the ratio of A divided by that distance squared. And it's measured in units of steradians, or steradian. Okay. Then you come down to the classic example, say, okay, I have my X, Y, Z coordinate system, take this back, and I do half of the sphere. And I say, what is the solid angle into half of the sphere? And that becomes omega is equal to 2 pi steradian, solid angles. Got it? We did that last time, right? Very good. So that's our summary. Again, radians versus steradians. Planar angle versus solid angle. What is it for half of a circle? What is it for half of a sphere, hemisphere? So many 2 pi steradians. Okay, now I need to introduce and talk a little bit, this is the challenging part, about the directional characteristics of radiation. So we go back and we reintroduce ourselves to the spherical coordinate system where we have x, y, and z, our traditional Cartesian. And then we think about this point out here. It's located at a distance r from the origin. So that'll be for the spherical. We're going to have r as a part that describes the location of a point. And then we're going to have phi and theta as 2 angles. So a length and 2 angles can describe any point in the spherical coordinate system. So we drop down to the xy plane, and we have a new line right here. And most of us, if you remember well from your calculus or other classes, would say, aha, that angle is theta, and this angle is phi. That's the way I learned it. That's the way a lot of students, I'm sure, learned it in their math class. But we are in a heat transfer class. And in the heat transfer class, the angle that is of most importance to us is this angle from the z-axis. So we would like to not use phi all the time. The textbook likes to use theta. So in our math class, we learned from the z-axis over, that's phi. Maybe you remember that. Maybe that's the way you learned it. Forget it for this book. Theta, that's the angle.
So they're both equivalent?
And then,
like theta 1
and then this one, we get rid of that from our math background and our math perspective, and we call this angle phi. So phi is from the x-axis, positive x-axis, to the projection in the xy plane. Okay? All right. Now, you had a comment or question?
Oh, wait, no, I thought they were both theta.
No, one is phi, one is theta.
Oh.
Yeah, that's their traditional. Now, you may have studied math in another book. Maybe they call it theta 1, theta 2, or phi 1, phi 2. Who knows what the mathematicians can do? They can do all kinds of crazy angular stuff. So anyway, so now the question is I'm really interested in doing an area integral. And I want to do the sum over all the little dAs. Remember this from calculus? And you're thinking dA, dA, dA. Don't change r, just change theta and phi. If I just make a little change, so dA is going to be something times a little change in phi and something times a little change in theta. What is it that gives me that dA from memory, from calculus? I want to see how many people can remember this, because this is the easy part for the next 15 or 20 minutes. And only, look, it's like you can get lost so easy, right? If we don't get this, we're really going to be lost. Professor's throwing up equations, and I'm just staring at them saying, oh, I guess that's true. I guess that's true. Can you remember what I'm trying to get here? So write it out. Yeah, sines and cosines and other terms. So write it out. Let's see who gets it correct. How many people? Well, I like to think of it as a product of two little lengths. And so if you just change, let's say, theta by itself, leaving phi and r alone, you would make a little arc like that, wouldn't you? And so that little length of that arc would be r d theta. So if I put an r d theta, that's kind of the little length of an arc. Then I need to think about perpendicular to that, making an arc this way. But I think about coming across, and this length of this line is r times either sine of theta or cosine of theta. This length right here. It's like the same. I didn't draw that very well. These two need to be parallel. This needs to be parallel with that one. That's still not very well, is it? Try and make them parallel, Professor. Okay, I'm trying harder. I'm trying. Okay, this is parallel with that one. And now what we're going to do is we're going to move d phi to make that arc, just like we'd move d theta. But I need to know what the length of this line is. So in terms of this right triangle right here, looking in 3D, what is the length of that line? R, the hypotenuse, times sine of theta. So r sine theta d phi. That's kind of like this length times that length give me the area. True? There you go. That's what I was looking for. Now you can test yourself and say, you know, calculate the area of a hemisphere. Okay, well, I'm going to sum up all the little d areas, so it'll be r squared times the sine of theta, d theta, d phi. It really doesn't matter the order there, but now I need to integrate with respect to theta. For a hemisphere, what is the smallest theta? 0, okay. What's the largest theta? Pi or pi over 2? Why is it pi over 2? I'm only doing hemisphere, not just the top half. And then for the phi, but the outer integral, phi goes between 0 and pi or 0 and 2 pi? 2 pi. And then you can do this calculus, remembering just a little bit of WORK, and you'll pick up that this is not 4 pi r squared, 2 pi r squared. The r squared just goes for the ride. Isn't that the area for the hemisphere? Little, you know, this is how you do it, right? Somebody says, I want to know, I'll try and redraw this a little bit. I want you to come down where theta goes between 0 and pi over 4. Isn't pi over 4 like 45 degrees? 45 degrees. And then I want you to spin it around the whole 2 pi and kind of see how that makes a cone. And now what I'd like you to do is tell me what is the magnitude of the solid angle omega in that cone. It's not the whole hemisphere, is it? But I could then calculate what is the solid angle in steradians for that problem. Let's go ahead and set it up. It would be omega. The equation is the area divided by r squared. That's our equation for the solid angle. The area would be the integral of with respect to d phi on the outside going from 0 to 2 pi, and then with respect to theta going from 0 to only pi over 4, right? Only pi over 4. And then inside we have the r squared sine of theta, and then you divide by the r squared. The r squareds cancel, and then you can calculate then what is that solid angle for that cone. It's not the whole hemisphere, it's part of it. Make sense? Okay. This is not very clear. I can't even read my own handwriting. What was that? This upper angle was pi over 4. That's right, pi over 4. So now we're getting refreshing our memory on how to describe solid angles, 3 dimensions, with this dA, with this r squared sine of theta, d phi, etc. Okay. Now the world only gets more lost. So here's a summary. You have the spherical coordinate system, 3 dimensions to it. 2 of them are angles. What exactly is r? Distance from the point to the origin to the point of interest. What exactly is phi? Not from the z-axis. For this book, it's from the x-axis to the projection in the xy plane. Theta, the angle from the z-axis to the line going from the origin to the point of interest. How to do a surface integral? If you wanted to, you could do a volume integral by varying r as well. And then how to do solid angle calculations. And omega is a over r squared, or d omega. You could just see it turns out to be. This is a big equation right there. The little solid angle is the sine of the angle times d theta d phi. Okay. All right. You are primed to continue. Hey, we got clicker questions. First clicker question. How many radians are in a half circle arc? So remember this little illustration for a long time. So we go out like this. That angle is theta is pi over 2. We go like that. That angle is theta is equal to pi. We go like this. That angle is theta is equal to 3 pi over 2. And then if you go all the way around, that angle theta is 2 pi. Did I do that okay? Does that make sense? So you ready to grade it? So a half of a circle, half of is just pi. All right, the next one. How many steradians are in a half of a sphere or a hemisphere? How many steradians? What is a solid angle going above? So we'll try and sketch this out again. Here's a little corner. It says here's a little chunk of area, and maybe it's emitting photons, and emits photons into a hemisphere above it. And so how many steradians, an angle, solid angle above that little chunk, itty bitty little chunk of area laying down there? Well, it's going to be 2 pi, isn't it? Isn't that what we talked about? It's 2 pi. 2 pi steradian. Well, now the world gets tough. You felt this class was real easy up to this point, didn't you? No, sir. Sorry, but I need to just cover this. I'm going to cover it and try to point out the main points to you. So they bring in this concept of radiation intensity. Well, I like the symbol I for radiation intensity. That makes sense to me. It has kind of funny units because the intensity right here, down here, you can have it for emission, you can have it for irradiation, you can have it for radiosity, the combination of emission and reflection. But the intensity has the most unique units. Here, just written for the emission, I sub E, it would be watts per meter squared. That makes sense. Per steradian. Okay, now it's going to be per solid angle. Okay, and it's measured in steradian. So watts per meter squared steradian, but that doesn't end the story because it's a particular meter squared. The meter squared, I would sometimes like to put a little subscript n, but that makes no sense. You have a subscript on a unit meter? That makes no sense. But maybe I do for myself personally to remind myself that it's the projected or normal area. So if I have a little area like this, and I have a direction not from the normal going up, characterized by theta. If I look back, this is my perspective, looking back this way, or if I look back this way where theta is 0, or if I look back this way where theta is almost pi over 2, almost 90 degrees. When I look back from the perspective of point, let's say direction A, it looks big. From B, it looks smaller. From C, it looks really small. Just think about it. I'm looking at an area and I see very small, but if I go up on top and look straight down, that's what they're getting at. It's the projected or the normal area. That is so confusing. Sorry, but that's the way the world is. Okay, so you multiply by pi. Pi, hey, we've seen pi used for both radians and steradians. This case, it's going to be for solid angle, steradian. And then you have E. Hey, that's more familiar. E, what was E for? Emissive power. So again, E, I would have preferred they call it emissive flux, but they don't. So anyway, but it has the units of watts per meter squared. You take a look. How do the units work? So steradian times watts per meter squared in the normal times steradian. The steradians cancel, and the units, just the meter squared turns into meter squared. So first time you look at this equation, you're thinking hemisphere, right? Why don't they have a 2 pi there? Because I really learned, the professor beat it into my head, there's 2 pi steradians in a hemisphere. Because it doesn't have it. It's not a typo. It just doesn't have it. I'm going to show it in a minute why there's not a 2. But at the first time your students see this, they say, oh, there's got to be a typo in the book. Good thinking, but I'm telling you it's not a typo. So you have the same thing where you have the intensity for irradiation as related to the this is irradiation, sorry, and then the radiosity related to that intensity for the radiosity. Okay. Only gets worse. Let me try and summarize here. So, if you see the I, what's that for? Intensity. Lambda, spectral, meaning it's a function of wavelength. E for emission. We did the same thing for the emissive power. Funny units? What they'll say is for a diffuse emitter, diffuse surface, this is not a function of direction, and we like that. We like that because it simplifies the mathematics. So if you look at figure 12.2, for a diffuse surface, like a black body is a good diffuse surface, they'll plot something that looks like this. And notice that this doesn't look like a function of theta. Theta is coming down from the perpendicular, and so this is not a function of theta. It's a uniform no matter what angle I go off at. Okay, now for a small emitting surface area, which is centered right down here, think of a little dA right there, you have the cosine multiplied by the cosine of theta gives me that projected area back. So if I multiply this intensity by this projection area of the surface located at the bottom there, and then I have a certain solid angle in that direction, then this is the spectral radiative flux. All right? So you put a double prime on this because actually this is not the flux up here. I bring the area over, I divide by the area, dA right here, then it becomes the flux. And so it's this constant for a diffuse emitter, cosine of theta, and the magnitude of the solid angle. That's why sometimes you'll hear that a diffuse emitter is described as having a cosine distribution for the emission. And then if you look in the textbook like at 12.4, you'll see an illustration that's saying, hey, simple surfaces look like this for the emission. And then you compare the two, and they look dramatically different. But one of them is talking about intensity. The other is talking about the flux, emitted flux. And here, as a function of theta, it tapers off significantly. Look at what does the cosine of theta do when theta goes to pi over 2? It goes to 0. The length of the little arrows going off come in at 0 at shallow angle, at theta equal to pi over 2. These are two consistent plots describing the same behavior, different language. It looks very confusing. Sorry. Let's move on. So if you're interested in, also the other thing is sometimes the book uses the double prime for the flux, sometimes it doesn't. A lot of times it doesn't. Like right in here, they don't put a double prime on something that definitely is a flux. So here is our spectral hemispherical emissive power, E lambda. So what you do is you would integrate over all of the angle, solid angle. You would have that cosine distribution, and this intensity for a well-behaved type of surface that we like to analyze is constant. That intensity is constant. So, but you expand out, what is our solid angle here? So now we have an integral with respect to theta going 0 to 2 pi, where you have cosine of theta, sine of theta, and then phi going 0 to 2 pi. All right. Let me see, I think it's right here. If it's a diffuse emitter, this is not a function of direction, just a function of lambda, so that comes outside the integral. And now we're just left with this integral. You can do that integral, bump, bump, 2 steps. I show it to you here, but this is what happens. Yes, you have the 2 pi from the 0 to 2 pi, but the inner integral gives you the half times the 2 pi, and that's why the 2 is missing. So E, the spectral emissive power, is equal to pi in steradians times I, the spectral emissive intensity. There's no way you're going to remember all that. There's just absolutely no way. It's way too much new math and new terms, and it's very confusing. No, it's like... So the moral of the story is, this looks like that. When you're talking about intensity, it looks uniform. When you're talking about emissive flux, it's cosine distributed. They're consistent. One has funny units of being per meter squared, where the meter squared is normal to the direction. One is simply the area without being a projected area. Let's blow through this problem. Huh? You ready to try this problem? And I worked out the solution, so it'll be a little faster. We have a small area down here, and we put it at the origin of a coordinate system. And it has a total emissive power of 4,000 watts per meter squared. So we use E, and it's for the surface, so it's surface 1. Don't really need that subscript lowercase e on it. E for emission, subscript 1. The emission is diffuse into the hemispherical space above the area 1. There's no directional preference. It's a diffuse emitter. Note that because it's diffuse, E is equal to pi I sub E. That's the equation we just had derived and used. Okay, relating intensity and the emissive flux or power. Determine the rate at which radiant energy is emitted. So we want to find this Q. Well, Q, emission from 1, is going to be that emissive power times the area. That's it. Go in small steps. I think I have like 4 pages for this problem. It never ends. So you just take the area and emissive power, 0.02 watts. That's radiant energy coming off, leaving the surface because of emission. What is the intensity of the emitted radiation in a direction directly above the surface, straight up, where theta is equal to 0? Straight up from the surface. Well, because it's a diffuse emitter, it's related to here, and so I sub E is equal to E, you don't even need that extra subscript on it, divided by pi, and you get the 1273 watts per meter squared steradian. That's the answer for part B. Then the next question is, what about at a particular direction of theta being 45 degrees, or theta being pi over 4, and phi being 45 degrees, or being pi over 4? Well, what's going to be the intensity there? Well, because it's diffuse, there's no directional dependence. It's straight up. It's the same going in any direction in the hemisphere. So answer to part C, same. Let's continue. So we have the total hemispherical area A2 of an enclosing surface having a radius of 0.5 meter above that surface A1. So little A1 down here, and then you go out a particular radius, and that's A2 enclosing going inside. Maybe I should draw it like this. There, A2. What is the surface area, the magnitude of the surface area, A2? Well, it's half of the 4 pi R2 squared. And you calculate it. Okay, next part. What is the rate at which radiant energy leaves A1 and impinges on A2? Well, let me ask this. If it's going to leave A1, can it go anywhere but hit A2? It's going to hit A2. This is funny terminology because we use this word impinge because we don't know what happens after it gets to A2. A2 could have a high reflectivity and a low absorptivity. We don't know. But at least we know it got to the surface of A2. That means it's impinged on A2. So basically it's everything that leaves A1 is going to get to A2. It's not like it can kind of curve and go through a hole like that. Photons go in straight lines. Continue this problem. For that small area, now consider a new small area A2. The hemispherical surface located at a radius of 0.5 directly above the surface. So we have this huge hemispherical surface, but just a little chunk of it right there. We're going to now call that a new A2. Right there, small, directly above the little surface. What is the rate at which radiant energy leaves A1 and impinges on the small surface right above it? Half a meter above. How do you calculate that? Well, you could do a couple different ways, but what is the solid angle from 1 up to that surface 2? You would say the solid angle is the size of A2 divided by, And so because it's directly above, you don't have any, it's not tilted at an angle. It's straight up. So I don't have to worry about an orientation of that area up there. So if the cosine of theta 2 is equal to 0, and then you just calculate so many steradians. Put that in here, where you have the intensity coming from 1. You have the normal projected area of 1. So now I get the magnitude coming off per steradian, and then I multiply by the angle. Notice because 1 is pointed straight up and 2 is pointed straight down, both of these angles, theta 1 and theta 2, are 0. That makes life a little easier. And you get that, hey, this is how many watts, not many, are leaving 1 and impinging on 2. Okay, what's the irradiation on 2 because of the emission from 1? Well, radiation is how many watts per meter squared of the area that's getting hit. So you take how many watts are coming up, you divide by the area of 2 to get irradiation, and there's the number. Boy, this is a tough problem. I think this is the last page of it. Sorry. Now, consider the small area A2, but guess what? It's now located at a funny location. It's tilted over here. But at least it's pointed directly back toward A1. But A1 is pointed still straight up, right? A1 is still pointed straight up. A2 is part of the surface of the hemisphere pointed straight back. You do the same thing. What is the rate at which radiant energy leaves A1 and impinges on A2? Well, you've got to get that constant intensity from A1. You look at the normal projected area from the perspective of 2 back to 1. I need that angle of this theta 1 right there in the equation. And then I need the solid angle. The solid angle didn't change from the previous work, did it? The solid angle, omega, is still the area of 2 that's normal, so I have the cosine of theta 2, and this is theta 2 up here, and that's 0. Divided by r squared. You get the same solid angle as before. Okay, because the distance didn't change and it's still directly looking down. But anyway, this changed right here. Theta 1 changed. It's now pi over 4, so the amount that leaves 1 impinges on 2 changes. And then what is the irradiation because of the emission? Well, you have to divide by A2, and there you go. Yes, sir.
Okay, I'm a little bit confused about
You're not the only one.
about W. How is it that the angle is?
Yeah, this is omega, and the same way of calculating omega, the solid angle here, we use the area, but it has to be that area is looking back at 1. And so it's hard to show these in 3D, but let's say my area is here and I have another area there. That area has a normal. I draw a straight line between them. This is my angle theta 2. But in both of these cases, theta 2 was 0. The first case where I had it at the top of the hemisphere, and the other at this location 45 degrees down from the top, because A2 is projected back and back. But I could have had a crazy one where okay, it's over here at 45 degrees, but it's pointed that way. Okay, well now I've got to consider theta 2 in my solid angle calculation. Yeah, you're going to have to think about it longer than that. At this point, you just say, okay, professor, keep going. Keep going. Sorry. I debated where they're throwing all this out. I don't know. I still don't know what to do because you don't have enough time to really plow deep and really cover it. But I want to give you the sense because when we get to the view factor calculation, it looks like, where did this crazy, crazy equation come from? Well, it came from here. So that's where. So think about that next chapter when we get to view factors. Okay, let's solve this problem. A little more doable. A little tricky on the math, but it's doable. Consider the directional selective surface having the directional emissivity. And notice I put this epsilon with what symbol on there? Theta. Okay. And so what they're trying to show is theta in this direction starting at 0, normal, straight up. And then if you go out 45 degrees, the whole way the emissivity is 0.8. But somehow magically at this angle, it drops to 0.3. Well, they do this so you can make the math a little more doable because you're going to do a setup and integration. Assume that the surface is isotropic in the phi direction, nothing preferential in the going around in the phi, just in the theta. And then calculate the ratio of the normal emissivity to the hemispherical emissivity. Often the hemispherical emissivity, they'll just give epsilon without any subscript. Here they've given it the symbol H. The problem is, I can tell you this is the epsilon with the symbol N. Look what the H and the N look like when I write them by hand. Talk about easily confused. A lot of times they'll just leave that hemispherical emissivity with nothing on it because it looks like the normal. All right, so they're asking you to calculate the ratio of epsilon normal to epsilon, hemispherical. Okay. How do I calculate the emissivity normal, and how do I calculate the emissivity for the hemispherical? One of these is really, really easy. Is the numerator easy or the denominator easy? Well, what does it mean to be the normal emissivity? That means the emissivity straight up. The normal emissivity is 0.8. How do we want to calculate the hemispherical emissivity? There's a number of ways of doing it, but what you have to do is say, okay, oh boy, here, I'm going to do it this way. I have it solved. I'm just going to talk through my solution because it can be a little confusing. So this hemispherical emissivity is used by multiplying by the black body emissive power to get the total off. Well, this is the total off, but if you said I want to calculate it from first principles, the emissive flux, isn't it the local emissivity, which could be a function of direction theta and direction phi, times the intensity? Now, the intensity, emissive intensity is a constant, so that comes outside the integral. Okay. And you're going to integrate with respect to theta and phi. Well, here's a cosine of theta and a sine of theta, so definitely you have to worry about that. And looking at epsilon, epsilon's a function of theta. But the phi you can do already, and so this 0 to 2 pi just ends up to be 2 pi. Well, you just rederived the equation that we have had already, that E is equal to pi times I sub E. Cancel those out of the equation. And we're left with the hemispherical emissivity is equal to 2 times the integral of the emissivity times cosine of theta, sine of theta, d theta, from 0 to pi over 2. Well, you bust that integral into two parts because the emissivity changes between 0 and pi over 2. It's constant. I'm sorry, pi over 4. It's constant. So from 0 to pi over 4, it's constant at 0.8. And then from pi over 4 to pi over 2, it's constant at 0.3. So you have two parts of this integral. And then at this point, dot, 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 I set it up. You just integrate. I didn't want to do that. You can do it on your calculator. How many people can do an integral like this on their calculator? If I said I want you to do the integral 0 to pi over 4, 0.8 cosine of x, sine of x, dx. Can you do that with your calculator? How about a couple people run it and then show me, see, 0.8. Instead of putting theta, you put x in there. Cosine and sine of x dx. Can your calculator do that? So when you make the calculation, this part comes out to 0.550. And then we already determined what the normal was. The normal is 0.8. The ratio of the normal to the hemispherical gives the 1.4546. Yeah. Yes, sir. This is 45 degrees. This is pi over. Did I say 2 or 4? 4. This is 4, right? Okay.
So pi over 2 will be
pi over 4 to pi over 2. That's all the way down here. That's pi over 2.
Yeah, but for the normal, right?
No. This is the little surface is sitting here, and it's flat straight up.
My bad.
Yep. Oh, there were the integrals done with a little help from a friend. The old friend, Wolfram. So one of the things we're going to do when we move to the next chapter, we're going to talk about gray diffuse surfaces. All right. What do you mean by gray? It's independent of the wavelength. Yes, we know that the properties are dependent on wavelengths. And we have to be careful when you have sun in the picture, because the distribution, the wavelength distribution of photons from the sun is a lot smaller. 0.2 to 2 micron is where it's most intense. But often if we have an enclosure where we have surfaces, let's say in this room, or something's warm over here and cooler over there, it's not that much of a difference in the wavelengths. So we're just going to ignore that and have a constant emissivity for the whole wavelength and a constant absorptivity. The properties are independent of the wavelength. So when you see gray, that's what they mean. Okay. The next is this diffuse. I've used that term before. We neglect the angular dependence. We know that it's quote-unquote cosine distributed in the emission, or it's uniform in the intensity. So somebody says, yeah, we have this wavelength-dependent property, the spectral distribution. If it's going to be gray, flat. Flat for the emissivity. Okay. And then if it's a diffuse, it has this nice cosine distribution to it. And that's what we're going to do. Well, I'm going to talk next time about a few applications, and then we'll move into chapter 13. Thank you very much for your attention.